welcome everyone today to a tour of our neighborhood, the neighborhood in space. And before I begin, I'd like to remind everyone that it's important to recognize why space matters and why exploring near us on planet Earth is really significant. This is where we will go as people. And since we live in space, what's happened to our neighboring planets is actually extremely germane to how we understand ourselves. In fact, one of the themes I will have today is things we've learned about Earth by looking at our nearest neighboring planets. That starts with Mercury and Venus, continues through our own moon, and goes on to Mars. So I'm going to be talking about that part of the solar system. And again, right now is a really pivotal time for understanding this region of the solar system, because this is where some of you may get to go. So it would be really pretty cool. It's been a generation since any human being has gone back to deep space. So we're going to talk about Mercury, the moon, Venus, the Earth, and Mars. These are the worlds that formed in the same neck of the woods as our planet. Now, a lot of people forget that the planets were all born in a rather tumultuous event about 4.7 billion years ago. A lot of energy, condensing matter, probably a lot of dark energy and dark matter that we don't understand yet. And it led to these planets. And one of the important things to remember is, while we look for other Earths, and here's our Earth, we have to remember that our Earth may not always look this way. So the hallmarks of our planet, the water planet, the life planet. Why is it named Earth? People always ask. In fact, water is inextricably linked to everything we do. But if you stripped off the water of our planet would look remarkably, in some ways, like the planet Venus. And so one of the things we do as we study the inner solar system is we do comparative planetology. So here's the Earth. I've unloaded the oceans. You can still see the islands in Australia, the 90 East Ridge, and many other features. And realize that our solar system is really a very interesting place because of how the planets have developed. Our planet developed into the water planet. Now, this little slide shows something rather embarrassing about how we see ourselves. Here's the Earth, and we have a time series for the planet Earth based on the history of life. We're a living planet. So we have Eocambrian or pre-Phanerozoic, and all these eras defined by fossils and things like that. Very important. We've developed similar things based on other indicators for the moon and now Mars and Mercury, and we have none for Venus. So our neighboring world, Venus, 90% of the size of our own planet, we haven't developed that kind of paradigm. This is a real kind of embarrassing thing. It would be like having a sister and not knowing what she really looks like. I don't know whether that matters to you, but to me as a planetary scientist, I worry about not understanding this planet. So we're going to come back to Venus. But we're going to start with the innermost solar system briefly, because we're learning about it very dramatically, move to Venus, the moon, back to Earth, and on to Mars. And I hope you'll at least be inspired by what we've learned in the last couple decades, because that's the lifespan of which a lot of the new data has really borne fruit. So right now, as we speak, a mission known as the Messenger mission is inbound to the planet Mercury. And this mission is one of the most challenging in the history of women and men, because it's trying to get to Mercury the cheapest, safest way, and actually orbit a planet where the temperature cycles are the most extreme we can ever imagine on a spacecraft. In fact, much of the spacecraft is a giant sun shield to keep the temperatures of the electronics so it can do its work. No spacecraft built by women or men has ever orbited Mercury. We've done 2 flyby missions back in the 70s, and now this mission has flown by Mercury twice, changing our view of this world that looks remarkably like the moon. The problem is, that's not the way Mercury works. But this mission won't arrive to Mercury to do its mapping until March 2011. So we're getting ready to unfold the real mysteries of a planet that's about a third the size of the Earth's, where we really don't know why its surface looks so much like the moon. There are theories why it has a magnetic field the way it does. Whether at the poles of Mercury there are actually ice sheets preserved inside craters. So the Messenger mission, built by the Applied Physics Lab, competed by NASA, is our new mission to that planet. And starting in March 2011, we will be peeling back the veil of how the innermost planet in our solar system works. This is the densest planet in the solar system. Okay? It's a factor of 40% denser than the Earth. Now, to get to Mercury, the Messenger spacecraft had to fly by and achieve a little nudge from the planet Venus. And that's what we do. We use the energy of the planets in the solar system to allow us to do what we do. This is one glimmer of the new data the Messenger is producing. This is a color visible infrared map of the cratered region of Mercury. The colors represent different chemistries. We see areas that are blue, coated with a different type of soil or regolith. We see these large compressive features. We think Mercury puckered because of the incredible thermal load from being so close to the sun. We see fresh craters where you see color patterns of the things that were ejected from them. So there's Mercury. I wish I could tell you how this planet put itself together, because we don't know. However, we have a mission to go. It's not a place we would likely send any of you. Temperature extremes would not be prudent, as a former president once said. So missions of exploration to the planets in this coming decade will revolutionize how we see our innermost planet, Mercury, and move on to other worlds. So this is just one little piece of the data about Mercury that we will have from global. So let me turn to the planet Venus. How many of us really think about Venus? Let me stop this for a second. Here's Venus in the night sky. You can see it tonight, a bright fourth magnitude feature. It's the brightest thing in the sky other than the moon. This is a winter shot from the last winter. What's interesting about Venus is a lot of astronomers are now coming to think, as we look for other Earths, we better keep our mind's eye open to Venus. What makes Venus interesting? Big, okay. Some of us might think that rocky planets can only get as big as those we have. To get too big, they break apart. They don't have enough internal strength. Secondly, it has a huge atmosphere. If you were standing on the surface of Venus, and I do not recommend that, very hot, if you were, the density of the atmosphere would be slightly, about 10 times less dense than water, and it's a gas. So it's actually a supercritical fluid made of carbon dioxide. So imagine how that kind of planet works. It's more like the gases coming out of the uncapped oil wells down deep in the ocean than anything we can imagine being here on planet Earth. So Venus, the morning star, sometimes the night star, I might add, is really an enigma. Giant atmosphere through our eyes, that's what all we see. A fuzzball. Cloud decks, we know those clouds now are partly comprised of sulfuric acid droplets and other nasty caustic chemistry. There have been more than a dozen missions by the nation formerly known as the Soviet Union to explore Venus. The United States has sent 2 missions to Venus, specifically one in the late 70s and one called Magellan. But this is the view you'd see of the super rotating outer atmosphere. Now, in the early 90s, the United States mapped 98% of Venus with a mission known as Magellan using something called synthetic aperture radar. These globe views show the planet seen by radar at about the scale of, the MODIS instrument on our Earth observing system, Terra. And here's a map, and I'll stop this, of one region of Venus, one hemisphere, and the big features you see here are each the size of the United States. They're huge. This is a giant mountain system with rift valleys and other features, and basically what you see here is color-coded topography with radar backscatter. The problem is the scale you're seeing is weather satellite scale. As planetary scientists, as people, we're used to the scale that we feel and touch and walk as geophysicists and others. So the scales we have for Venus aren't enough to tell us what made that. Are all these blue areas places that are low because at one point they were oceans? Wouldn't that be cool? Today, the present conditions for Venus would not support the existence of liquid water. The average surface temperature, 450 degrees centigrade. Average surface pressure, about 100 bars, okay, 10 megapascals. This is not the kind of place you'd like to go. Not the place we're thinking about for human exploration. However, in the story of Venus is a story that we need to be aware of for our own planet. And this is very important. So there's the visible Venus. Big atmosphere. The actual outer atmosphere super rotates. In a period of 2 days, the whole atmosphere goes around, sort of like our Earth's atmosphere. The lower atmosphere of Venus that you see here through the eyes of radar slowly rotates retrograde. So in fact, a day is longer than a year on Venus. Imagine that. Why Venus doesn't have natural satellites? We don't know. Venus doesn't have an obvious giant magnetic field. Why not? Big, hot planets tend to have those. Earth, Jupiter, Mercury. What's going on? We don't know. What made Venus' climate system today hellishly hot, caustic, not friendly to life, possibly superoxidizing? What made it that way? Was it born that way? Very unlikely. It's hard for a planet to be born that way for many reasons. So what made it go into a runaway situation? Again, we don't know. The last mission to Venus was by the United States, which made these beautiful maps, was in 1991 to 1994. So I show you all this stuff about Venus because it's really, really an important end member for how big rocky planets work. And some scientists at one point thought that all these mountain areas on Venus were like the mountain ridges of the ocean floor. And Venus is ripping itself apart and exuding energy through these chasmata, these canyons or chasms, the way the mid-ocean ridges do on Earth. Now, Maybe some of you have thought about mid-ocean ridges. I think it's important to say that our planet regulates its internal heat balance by a system of 45,000 kilometers of mid-ocean ridges, which come on land in Iceland, a little bit in Africa, and we see the hotspot traces of them in Hawaii and other places. If we did not have that system, our planet would be a lot hotter. The crust would have to conduct more of the energy of this big hot interior. That's not good. Would not be as good a place to live. Well, here we have an area, the United States would fit right here. Here we have an area called Avda Regio, part of Aphrodite on Venus, connected by all these deep canyon systems, perhaps like mid-ocean ridges, or I'm sorry, mid-ocean trenches. But again, we don't know, because the scales we see are inadequate to resolve that. There are measurements of the Venus atmosphere measuring the isotopes of hydrogen that suggest Venus once had global oceans that would have filled all these low blue areas. Oceans of water. That's a possibility. If it did, Venus may have been a habitable planet. In fact, early in the history of our sun, some scientists think the sun was less luminous, a little less hot. It sort of flares for a while, cools down, and then it, well, eventually dies. That Venus would have been right in the habitable zone. Imagine that. Two big rocky planets with oceans in the habitable zone. One went one way, the other went the other. So as we look at the Venus atmosphere and the Earth atmosphere, we're reminded that there's a lot of the story at scales that we people need to get our grips on. So this is an artist rendering, because we don't have any data, of what the hilly ridge plains of Venus, these areas we call tessera, might look like. There's even new data suggests Venus may be erupting today, like the volcanoes on Earth, like the ones at Eyjafjallajökull in Iceland or other places. This is a possibility. Again, without robotic remote sensing, understanding what these weird landscapes, here's a giant impact crater on Venus, this is the spiderweb terrain. Understanding all this stuff is hard. I mean, if I showed you those maps and pictures made by landers that look like this, you can recognize the Russian writing on those landers, you'd wonder. In fact, the longest surface operation on the planet Venus in the history of humans that made this image was for roughly 2 hours. So imagine having to do all your work, whatever you're doing, in 2 hours. It's kind of like a sprint. Here you see the lander view from the Soviet missions in 1982, CCCP, USSR, lens cap, of course it fell off, good thing, and the view from the other one. So this is our complete data set. You've just seen it in 10 seconds of the surface imaging of the planet Venus. In contrast, for Mars, we have a terabit of images from the rovers and other things. So let me stop for a minute and just put it in perspective. Biggest other planet in our solar system that's rocky, Venus. Jupiter's a gas giant, of course, Saturn, and others. We know less than we did in perspective about Venus than we did about the Earth probably in the 1940s. So in the space age of the last 51 years, we haven't filled in the textbooks on Venus. Who knows what it might tell us about how our own climate system works. So here's Earth, large climate system recorded in the atmosphere. This is from a shuttle flight, and you can see our moon. Now, one of the things interesting about the Earth is we have a very large natural satellite. Now, a generation ago, when I was younger than you guys, we actually sent multiple human voyages to the moon. And you might say, why did we do that? It was brash, brave, bold. We went to the moon because, in fact, it was better for us to develop the systems for people to go fly to the moon in command service modules with capsules than robotically. We actually, those days, did not have the robotic capabilities to do what we do today. You guys have grown up in a generation of robotic IT infrastructure. When we went to the moon and saw landscapes like this, from the field of view you'd see flying over, we went with human eyes the first time in December 1968. So the Apollo program took us to the moon. And you might say, well, you know, what did that do for me? Well, aside from Tang and Teflon, what it did do for the United States was develop not only precision navigation, which we use now, been mapped into GPS, but it also developed the first large-scale integrated circuits, which we needed to go to the moon. Here you see Buzz Aldrin coming off the lander on the first visit to the moon on Apollo 11. We, of course, erected aluminum guy wire flags. It was a big engineering challenge to do that, by the way. We developed the highest land speed cars on another surface, the lunar roving vehicles. And we went to the moon and brought back a legacy of a history of another world in 890 pounds of rocks. We actually set amazing speed records with these things they drove. We left our name tags on there. There's John Young's Apollo 16 mission. This is the legacy of human exploration. In the first decade of NASA, we not only built weather satellites, started missions to explore the outer solar system, but we sent people to another planet. Now, how many of you realize the last time any women or men ever left the protective magnetosheath of our planet was 1972 on these missions? Now, let me stop here. This is a famous picture. In November of 1969, the second of the Apollo surface missions, Apollo 12, Commander Alan Bean went and sampled the lens of a robot we had sent to the moon 3 years before. You might say, okay, sounds pretty cool. He actually landed about 180 meters from, with his lander craft, the LEM as it was called, 180 meters from that, across a distance in space of 400,000 kilometers. Now, do a little math, pretty good navigation to go that far in deep space and land that far. We were then in a missile race. Apply that to the missile race of the late 60s. I think you can all do the math. This was one of the greatest technology feats in the history of the 20th century. Precision navigation on another planet across the abyss of deep space. We actually discovered that the lens of that vehicle had been contaminated with a type of bacteria that survived 3 years in deep space, no air, water, deep space radiation, solar flares, came back, put it in a petri dish, cultured it, grew. So life is tenacious. And we worry about that as we explore planets where we're asking, are they alive? What if we bring ourselves to those planets and then we discover that we're there? Okay, that's a great result. So as we think about astrobiology, where life works, even on the moon, an absolutely airless world throughout its history, we brought life there, not only us in Commander Bean, but in others. So this was a major thing. This is my favorite picture of the moon. This is 6 kilometers looking back at the spacecraft that carried Apollo 17 to the moon across the hills of Taurus Littrow. That was the walk-back distance. If all had gone bad, the guys had to walk back that far to get home. Of course, we drove around, we sampled rocks, we did a lot of geology. I'm a geologist. This is really significant to me. One thing we learned about the moon, it's old. The first rocks told us, famous picture, that when we look at the moon, we're looking at a surface that's frozen in time. It's a fossil planet. Everything you see, including the seismic network we stood up, is recording a history of something like 3.7, 3.8 billion years. How many rocks have any of you seen that are that old? None. The first billion years of Earth history has been wiped. So the attic of the Earth is recorded in the story on the moon. And that told us a lot about ourselves. Here's a famous picture as we left the moon for the last time, coming home to the Earth. So that's the last time people have gone into deep space. That's a bold thing. Now, this is what it looked like landing. Of course, you've all heard the story of what Neil Armstrong had to do to free fly his vehicle. I love to show the drive. The land speed record here was about 16 kilometers an hour. Just for scale, the Mars exploration rovers move about a 50th of that in their speed. So these guys were trucking. They actually had to build new hubcaps a couple times because they went a little fast. But again, it was really a great way to explore. In their trips, and you see how rocky and bumpy it was going along the moon, they actually covered on one mission in Apollo 17, 27 kilometers. Now, stop here for a minute. 27 kilometers in one 7-hour extravehicular activity event. Have we gone 27 kilometers on Mars with the Mars exploration rovers yet? No. And we've been driving for 5.5 years. So, one day, 27 kilometers. Out, back, collect the rocks, come back. We people like to explore fast, particularly in tough places. This is the now, why me generation. That's important. When you move things to the robotic time space, you can freeze time. You can move more slowly. And so one of the things we do in exploring planets and the deep sea floor is we change the time scale. So if it takes a week for a rover to go 100 yards, well, too bad. We'll wait. The robot is doing the job. So the moon now is a new place. It's a new place because of an armada of robots that have gone to the moon in basically the last 5 years. It started with the Japanese. A brilliant mission known as Kaguya, also called Selene, has been at the moon. It ended its mission last summer, but it produced beautiful HD TV quality fly-arounds of places on the moon. These are some of the biggest mountains on the moon. These are 4-kilometer high central peaks of the crater Tycho. The crater Tycho, we think, was formed about 95 million years ago when dinosaurs roamed the Earth. So this is a real mountaineering peak. John Grunsfeld, the astronaut who served us to Hubble, he'd like to go climb the Mount Tycho, or whatever we call it. But this data was collected by the Japanese mission that started in ushering ourselves back to the moon. So why go back to the moon? Everything on the moon happened a long time ago. The reason is the moon is a history book. On Earth, we're interested in what happened since the dinosaurs, since we've roamed the planet. But on the moon, we're interested in other things. For example, Before the mission known as LRO that NASA Goddard launched, this was the best topography of the moon. If you wanted to land there, your accuracy of that landing site was good to 1,000 feet. So imagine coming in to land in Washington, saying, well, we hope the airfield's within 1,000 feet. Wouldn't be the safest landing. Now we have new maps that not only look better from an instrument built here at NASA Goddard on the Lunar Reconnaissance Orbiter, but the quality vertically is good to about a foot. So we can now plan landings more safely. We can go to the interesting places and land. So one of the things we're doing now with NASA's return to the moon with robots is mapping the planet at the scale that you guys can choose to use if you want to go back to that planet. We didn't do that with Apollo. We went with elegant engineering and brute force to the safest places we can get to. Turns out the moon's also interesting for another reason, probably something you've seen on Jeopardy. There are places on the moon, you see their names floating around here, that actually are permanently shadowed from sunlight. That means they are the darkest, coldest places, inside some of these craters at the South Pole named for famous explorers, that we ever understood. In fact, inside those shadowed areas, it's colder than the planet Pluto, or I should say, the dwarf object formerly known as a planet, Pluto. So here's the moon. Inside those cold places, you could actually entrap frozen stuff like water, hence ice, and the ices that are trapped could record a couple of billion years of the collisions of the moon with comets. Now, do we care about comets? Yes, because some colleagues, scientists believe, that comets help seed our oceans with some of the chemical building blocks that led to life. So here's the telescopic view of the moon. We now see the moon in 3D at the scale where you could drive a car across it and plant landing strips. We've gone from the era of looking at the moon through telescopes to being there in person. Our Lunar Reconnaissance Orbiter is there now, about 45 kilometers above the surface, mapping the moon at scales where there's that crater Tycho, where you could plan a landing site on the peak of a mountain if you wanted to go there. One of the revolutions about the moon we learned from the Apollo missions that we can now show you in depth from these new maps is the fact that it has all these craters, these circular depressions, is actually important. Now, why should you care about craters? I happen to study them. I'm sorry, it's a boring thing, but my wife said someone has to do it, so I'm doing it. This here is the topographic expression of a 1 trillion megaton explosion that shocked the moon 4.2 billion years ago that formed what's called the South Pole Lake and Basin. The impact collision there was so intense, it probably excavated the lunar mantle through the crust, brought up stuff that we would never get to. We want to sample this basin. We didn't even know it existed until these measurements. We see these big cosmic collision scars on Mars, on the moon. We're looking for them on Venus, haven't found them. And they're actually great windows into the history of planets. So now we see them. We know where they are. We can figure out how to sample them. So all the data you see here was collected in the last year. The Lunar Reconnaissance Orbiter has collected data for the last year on the order of 78 terabytes of data. That's more data for any object in the history of solar system exploration in one mission in 1 year. It does pay to have your own ground receiving station, if you wanted to know that. So one of the things we're really interested in is if you were to go back to the moon with people, where would you go? This is what the sun would do in the sky, rotating around one of the sites right here on the rim of the Shackleton crater, where some engineers think we could set up stations for people to live and have sunlight basically all but 60 hours every year. And this shows the shadowed areas which have not seen sunlight in 2 billion years. So we look at these places and wonder. Now, the other thing we've done, which is kind of history in the making, is we've actually taken photographs of the places where we've been on the moon. And these photographs are basically about 3-foot resolution. You can see the blast spot. These are where they actually walked on the moon. You can see the trails. Now, remember, this all happened in 1969. So in the 41 years since all this happened, nothing's changed. This is a planet where things work slowly. You can see the stations, all the features. There's the weird crater. This is the traverse they made on Apollo 14, the longest walk made by people. The Apollo seismic network. Here's another one from Apollo 15, all the drive paths. You see the 2 wheels. We can now see what we've done to other planets. I mean, this is something you'd expect in the Smithsonian. We haven't brought back these pieces. Here's the Challenger descent stage. That's what brought us to the moon and then blasted us off. There's our flag, a little shadow. So now we look. We found the collisions of the first Russian probes on the moon. We could, if you were there, we could probably see you waving, but we're not there, so couldn't do that. We've, of course, counted a lot of rocks. I won't bore you with those and move on. But I just want to point out that we've done a lot at the moon, and it's kind of a cool place. One of the other things we've observed on the moon, and I'll quickly cut to this as we go, is in fact there are places on the moon that are so cold they're off the charts. Some of these shadowed areas are 25 degrees Kelvin. That's cold, folks, colder than liquid nitrogen. We didn't know that. We've measured again the topography, and just a little summary of what we've already done with this mission known as LRO. Starting in September, the Lunar Reconnaissance Orbiter, built right here, some of you may be working on it this summer, will transition into a science mode. Now this is a view of the place, right in that shadow, where the L-Cross collision occurred last October 9th. We smashed a leftover piece of a rocket and watched what happened when we collided with the moon. And guess what? It kicked up the kind of stuff that can be vaporized, like we think water, hydrogen, and even mercury, the kind of mercury in your thermometer. So these are views of the moon as if you were flying in a helicopter across the surface at about, in this case, about 50,000 feet. Pretty cool. This is the L-Cross experiment. It was co-launched with LRO. It took its time getting around to the moon. This is the flight dynamics that is something that's pretty amazing that we can do. We threaded the needle of the rings of Saturn. We went to the moon with it, and in fact, you can see what we did to get there. So there's LRO went straight. This thing looped around for a while, actually for almost a year, and then collided with the moon. And the experiment was incredibly successful. Research papers are coming out in Science Magazine in the next month. So we're very excited about that. But L-Cross was an example of women and men using ingenuity. They had something. We used LRO to target where to go, which we did, and then we collided the spent upper rocket stage with a small shepherding satellite with the moon, making a crater, exposing dirt, vaporizing, we think, ice, and measuring its signature. So you might say, well, were we allowed to do that? We were. As a planet that we do not think is a life-bearing planet, this kind of experiment is allowed. This kind of experiment would not be allowed on the planet Mars, because we think Mars may or may, well, possibly had life. So anyway, the moon has come alive as a new world. We have another couple of years of mapping with the Lunar Reconnaissance Orbiter. We hope to send landers to the moon. This just shows an animation of what happened last October. And in fact, we actually impacted in a place in shadow, produced a plume that was received and measured by LRO on orbit with its far ultraviolet spectrometer. So pretty cool stuff. Mission was a total success, and I'm really proud of the team that did that. You can just see that again. Now, another thing we've done in our exploration of the solar system is visited near-Earth objects. And in 1999 through 2001, a little tiny satellite about as big as this, called NEAR, Shoemaker, visited one of the biggest near-Earth asteroids known as Eros. It mapped the surface of this rubble pile of silica-based rock, and then it docked with the surface. And one of the dreams we have for people going into space is, instead of leaping straight to Mars, actually going to visit near-Earth objects first. Why? Because they actually collide with Earth and are relevant to the history of life. Two, there are hundreds of thousands of them, of which 90% are uncatalogued. They're everywhere. There will be a close encounter with one in the year 2036. It'll come within the orbit of the Earth's moon to Earth, called Apophis. So we care. One of the theories now, one of the studies that we're doing in the agency is, what would it take to send you all to a near-Earth object where the surface gravitational acceleration is such that if you took a step, you'd escape? Be a great weight loss clinic, you know. You go from weighing 100 pounds or 150 pounds, and you weigh 5 ounces on one of these small objects. It would be kind of neat. This is an artist rendering of what a first human mission to a near-Earth object could look like in the mid-20s. We could actually go to the kind of objects that we think are made of the building chemical blocks that could have helped seed life on planets. There are a class of these small objects, called near-Earth objects, that are, we think, made of carbonaceous materials. Those things certainly collided with early Earth and early Mars. Now, the interesting thing about this is we don't know enough to design this mission now, so our artists and engineers have come up with what we'd like to do. But since we haven't characterized these objects, except for the one, we don't know what we would do. But one of the things we feel we would have to do is we wouldn't go land, because there's no landing on an object that you bounce off of. I mean, it'd kind of be hopeless, almost futile. So what we would do is send people down on rope chains, and they would go and tether themselves to the surface. It's kind of like climbing the wall of a rock, you know, in the Grand Canyon, but knowing that if you fall off, you're going to float away. I mean, a little less risky, but you wouldn't want to float away in free space. So here you see a couple of women tethered to a piece of an asteroid. Again, we don't know that they look like this. So one of the things you're going to see in the next decade is missions to asteroids by robots to see what they're really like. Sampling them, understanding how to operate around them, it's a very important step. So you can see here's a woman and a guy coming off on their tethered thing, flying back, little rocket packs, back to the mothership to come home. So this is an artist rendering of what might happen. Some of you could be in the position of helping to make these kind of missions happen. So I want to remind you before I go to Mars that we actually have a constellation of 14 satellites in Earth orbit. And you might say, well, what's NASA doing for global warming, for climate change? We are doing a lot. Very often the things you see on the Weather Channel every now and then, the weather like today, it's going to rain again, sorry. Or the Snowmageddon we had this last winter here, great fun, by the way, is informed by these satellites. We actually can produce a global mosaic of the entire Earth's surface every day from the Terra spacecraft. We study the winds, we have exploratory missions, we study the nature of how the oceans work. This is part of what we do here at NASA Goddard. We do it in partnership with other centers like JPL. So the Earth is a planet. Why should we neglect it? And by watching how it moves and changes, particularly its atmosphere, oceans, and land cover, very quickly, we get a little impression of how our own planet works. Now, one thing NASA's done in the last couple years, probably none of you heard about, but I have to feel that I talk about it. We've actually mapped the polar ice sheets in exquisite detail. This is a flyover rendered completely by computer of the calibrated Landsat mosaic of Antarctica. It's a fingerprint for the state of ground-covered ice for our planet. If that changes too much, that tells us something. We've watched over the last 20 years the retreat of not only mountain glaciers, but of the ice sheet in Antarctica. Pieces the size of Delaware have broken off. This is a concern of ours, because the runaway rate of these changes may be normal, but we haven't experienced them as humans who are aware of it ever in our history. You know, in the Middle Ages, I think people probably weren't aware of anything. But now they are. We are a living planet. We talk, we breathe. And when you see recessions of the ground lines of ice that are so rapid, we get worried. The other thing we're able to do is take stock of the biological health of our planet in 2D. This map of the ocean color and related quantities allows us to see the state of health of biomass growing in the ocean. And these big dark purple and blue zones are areas where there are less living things. And we can do these kind of mappings from missions like CWIFS, from our MODIS, routinely. You can see blooms of high biological production in the oceans, of course the greens on land, and the deserts. One of the things NASA wants to do in the next decade is do this in 3D. What's the biomass of the forests? How is the carbon system changing? This is critical. And so we have mission plans to do that. So the Earth is a planet. It's a living planet, the only one we know. We're looking for Earths. So here's Earth in the living planet stage. And this is what we do in our Earth Science program, again, superimposed on that. So what about Mars? Everyone asks me, was Mars ever like this? Is Mars truly the astrobiological planet that we all know and love? Well, for the last 15 years, all of you who have cared to notice have witnessed the greatest robotic era of exploration of the planet Mars in the history of women and men. We are at a time of every time we go, it's a new revolution in how we see the planet. This fly around I'm showing you now was something I dreamt about when I first came to NASA now 25 years ago. This is Mars in 3D. The hot colors are high, the other colors are low. This is the South Polar Ice Sheet. We now know it's made of water ice. Before this mission, the Mars Global Surveyor, we thought it was all frozen carbon dioxide, dry ice. It's water. Sorry about that, folks. This is the North Polar Ice Sheet, the great hockey puck. Not a puck, really, but it's a large ice sheet like Greenland on Earth. I don't know if any of you have ever been to Greenland, but if you've flown over it, this is about the same size. Spiraling canyons. The Mars atmosphere exchanges itself with the surface. 25% of the atmosphere freezes out and then sublimes into the atmosphere every single year on the planet Mars. The mass balance of the polar ice sheets, predominantly made of water ice, are a critical barometer of climate history on Mars. We think Mars has gone through monumental climate sweeps, partly because its rotational axis, the angle axis of obliquity, as some of you may know, actually doesn't wobble a couple degrees like Earth's, which causes huge climate changes over scales of 10,000 to 100,000 years. On Mars, it wobbles by 20 to 30 degrees. So imagine if the Earth's axis, went like, whoa. Well, we would have a different climate state. Trust me. Physics does not lie. People try to legislate it, can't change it. So Mars has gone through wild climate change. And we now know that by measuring things about the planet, both in 3D and in the atmosphere. So we did this mapping here at Goddard with our partners at JPL as part of the Mars Global Surveyor mission. We now know any place we want on Mars, good to about a foot or two. That allowed us to send missions to Mars that before this mapping, and before we got to look at the biggest volcano in the solar system in 3D, would not have been possible. I'd like to show this picture for a minute. This is Olympus Mons. It is 6 million cubic kilometers of rock. It has around it a large cliff line, an escarpment, that is 3 to 4 kilometers high. When we first saw that in photographs in 1972, people said, oh, geez, I didn't realize that would happen. Wonder why? And they did a few calculations. They realized big giant volcanoes are too heavy to hold themselves up, and they collapse. So people decided, well, why don't we see that on Earth? I wonder why. Let's go look. We looked all around the big volcanoes of Hawaii. They all have big flank collapses like that, only they're underwater. Never saw them. What happens if a whole side of a volcano, like all this part, collapses? On Earth, it moves stuff. If it's underwater, what's it going to move? Water. What's the water going to do? It's going to turn into gigantic tsunamis. Gigantic tsunamis that could actually affect the coastlines of the Pacific in the United States, in the east from other places. So we discovered by looking at Mars how some aspects of our own planet work by just observing them. So this is one of the discoveries where planets informed our own history. On Mars, we have a system of giant volcanoes. We also have Mars seen now here, where we've taken topography and imaging from one of our satellites, Odyssey, and put it together. We do have little mini tornadoes on Mars all the time. And what we also have on Mars, which is so staggering, aside from impact craters, is the solar system's largest canyon system. You might say, well, how did little old Mars, 38% the size of the Earth, okay, not big enough to have worked the way the Earth did, produce a canyon system here that makes our own Grand Canyon dwarf in comparison? How did it do that? Why does Mars work so different? Here's Los Angeles for scale. You can see 7.2 kilometers. Our Grand Canyon, I'll show you in a minute, would fit in one of these little spur canyons. And if any of you have been down in the canyon on a mule, I think you'll know, that was a joke. The mules are a little bit nasty at times, but they are fun, actually. So this is a canyon system that goes 3,000 kilometers across the midriff of Mars. Why is that? What ripped apart this planet with a crust and possibly with a water history unlike anything on Earth? That's one of our conundrums, one of our enigmas. So here we are flying up one of those canyons seen from Odyssey and our Mars Global Surveyor. The Grand Canyon for scale would fit right here. So if any of you have been there, it's pretty big, pretty dog. You don't want to fall in. They do lose a few every year, I've been told. But so one of the things we learned about Mars then, the scales of things that operate on Mars, climate, are different. So in 2003, we launched a pair of twin rovers, golf cart-sized rovers, solar-powered, to get the Mars program back to the surface. We intended them to last 90 days. Today, basically 5 3/4 years later, they're still going. Pretty good design by our engineers at JPL. These rovers, in moving at the pace of a giant tortoise about an hour a day, that's their pace, have uncovered things about Mars that you can only see from the surface. First thing they learned, crawling along the edges of things like craters, there's the Opportunity rover, is that there is a history of water on Mars in all of the rocks. While it looks as dry as a bone, actually, if you look closer, this is the Victoria crater that we spent a year at, as seen as we started the drive around and went into the crater. We realized in the layers exposed in this crater and in some of these rocks are history of minerals that can only be made in the presence of water. We have no physical way, good old chemistry doesn't lie, to make them. So while Mars may look as parched as anything we'd ever want to think about today, the history of water is there in the rocks. And if we could go to places more interesting than these flat parking lots with a few craters, we could get to places where the history of water in the rocks could lead to preservational environments, the kind of which on Earth preserve evidence of life. So our next mission to Mars, I'll show you in a second, is actually after that. Can we go to places better than this that expose Mars so we can ask, could Mars have been alive? And if it was, what are the signatures? I mean, imagine that. Are we alone? No. There were the Martians, whatever the Martians look like. So here you see Odyssey crawling down into Victoria Crater. Today it's heading far south. This is one of the great success stories of robotic exploration. Although it took 5 years to go as far as a couple of men and women could go in a couple of days, we did it for the cost of a James Cameron movie, not for the cost of something bigger. So robotic exploration is important. Now this funny view, you might say, is about as boring as you can see. This is the real Mars. Swales of dust-like dunes and patches of, we think, sulfate-rich rocks covering about 10 or 15% of the planet. This is the real Mars, the Mars that humans would interact with. Problem is, these little dunes of fine talcum powder stuff aren't too good for driving robots in. They can get stuck. We got stuck for 40 days in this stuff with Opportunity. We backed ourselves out and escaped. But we have to build better mobility systems so we don't get stuck on the real Mars. Now, this funny picture is one of my favorites. I thought I'd share with you for a minute. After driving around Mars in one place for a while, Spirit dug around its wheels. They're about this big, about a year ago, and discovered lots of basically silica in the soil. The white stuff is basically pure silica, leached out of rocks by the action of water. So in this dry place, perhaps less interesting than where Opportunity's been in Meridiani, we've uncovered the signature of water. We found minerals like goethite, for those of you that like minerals, again, made in the presence of water, typically on Earth, we think on Mars. So the dry Mars we see from remote sensing, from orbit, is actually telling us a history of water on a planet that I would call a water planet. Today, the history of water on Mars is masked by rocks like these that are typical volcanic rocks. These are basaltic rocks, we think. And so it's beguiling, as Shakespeare once said. So it's important to remember, every time we've gone to Mars, we thought we got it. Yep, Viking going to Mars, going to find life. Nope, not there. Go back to Mars, again with other missions, and this is the launch of our Mars Reconnaissance Orbiter, and we thought we'd see something, and we got something else. So in 2005, we launched the MRO, the Mars Reconnaissance Orbiter. And this was one of my dreams, to go to Mars with the kind of eyes and spectrometers that could see Mars as if we were walking on the surface. And MRO got to Mars. It has a big 65-centimeter optic flying right down it there. And it arrived at Mars, and it changed the way we see the planet. Typically, we see Mars at this scale, craters. Then, thanks to the Mars Global Surveyor, we saw Mars at this scale. Now, we see Mars, if you look in at the next frame, for now 20,000 places. Not at this scale. This is the typical scale that we get from the MRO, but at that scale. We can now fly over the surface of Mars for tens of thousands of places as if you were in a helicopter zipping over. At that scale, geology can become definitive. And this happens to be a gully site where these gullies once erupted fluids, Newtonian fluids, probably water. We don't absolutely know. They're stained by dust. But we've discovered more than 6,000 of these kinds of gullies, some of which have changed in the course of the last couple years. This is the polar ice cap of Mars showing the chock-a-block terrain. And this white thing you see here is a little patch of ice exposed. We do this routinely. So MRO has changed the way we see the planet. The other thing we've done with MRO is used a radar sounding method to slice right through the polar ice caps. What do they look like? And so using 20 megahertz wavelength radar, built in this case for us by our friends in Italy, we've been able to slice through sort of the way MRIs do our body and see the layering structure of the polar ice caps of Mars. They're about 3 kilometers thick. They have layers hundreds of meters thick. They run a scale the length of half the United States. This shows what we thought was happening, that in fact these ice caps are built up episodically. And that's a really important discovery. Within these layers could be lenses of preserved liquid water. Those could be the places where you'd want to go to seek signs of active life. Finally, we've also found in equatorial areas near the equator of Mars, with imaging and radar, that under the dust cover there are buried glaciers, tropical mountain glaciers near the equator on Mars. So, MRO, the Mars Express, the Mars Exploration Rovers, the Mars Global Surveyor, they have changed how we see the planet. We would now describe Mars as a water planet that could have preserved the biological signatures in rocks of life. Let me turn to Phoenix. In 2003, NASA said, okay, world community, all of you could have bid. We're going to have a competition like the Olympics to pick the next mission to Mars, Mars Scout. And after a year and a half of competition, a landed spacecraft developed at Lockheed Martin and Jet Propulsion Lab in Arizona went to Mars to ask, what is the ice really like up near the North Polar Cap? Why would we care about it? So it landed, it popped up its cameras, and it observed Mars for a period of 150 days from the edge of the North Polar ice cap. And during descent, we watched the descent through the eyes of MRO. And there is the parachute with the lander seen from another spacecraft as it descended. The geometry of that was rather challenging, but we actually managed to pull it off. We landed, this is the foot pad, and right underneath the lander, after the landing rockets settled, we found a patch of ice. Now this is what the North Polar region of Mars looks like. In the far distance, you can see the sun setting during the 150 days as we went from summer to fall. We watched the wind blow. We tracked the star with lasers, the sky with lasers. And we saw patches of ice exposed and evaporate as part of our measurements. We ingested materials and detected for the first time definitively the molecule water on Mars with a chemistry lab. There's a patch of ice under the lander. So Mars, where we thought there would be ice, we validated it's there. If you start to look at the little white tinge here, that's frost forming on the surface as we come out of Mars' northern summer. So the winter sun set, it got cold, the solar panels got no light, the batteries died, and the mission essentially froze. But we generated 100 gigabytes of data in a 150-day mission for the price of a small blockbuster movie. There's the Wall-E-like camera eyes saying goodbye to you from Mars. Our next mission to Mars is the one I'm most excited about. And I get excited pretty easily, as you can probably tell. We've been dreaming of this since 2000. When we broke the program for Mars, we dreamt of sending an astrobiological rover to Mars. In this case, that we will land in the summer of 2012 with a rocket-powered helicopter system known as a Sky Crane, developed at our Jet Propulsion Lab. This rover is as massive as a Mini Cooper car. How many of you have ever been in a Mini Cooper? No? Yes? A few hands? Okay. They're not tiny, right? I mean, football players might not prefer them. But anyway, we will not even land the spacecraft that gets us there. We will drop the rover down on a winch, and then we will measure rocks without even going to them. By firing a laser beam and ionizing the surface of a rock, we will measure what they're made of. This is, like Star Trek does Mars. That will help us not have to drive everywhere. We will drill up to this deep into rocks and then bring the samples sort of with this crazy-looking extrusion process. Reminds me of my dog, but anyway. Bring materials into the vehicle. And inside the vehicle, here at Goddard, we've built something called SAM. And everyone asked me why Paul named it SAM. Could have been Sue. Could have been Jim. But SAM is the Surface Analysis of Mars package that will allow us to measure chemically whether there are the biological building blocks of life. We can actually measure the carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur in soils and in the air at levels that are better than those we could measure in labs when I was in graduate school. And now we have a robot lab we've developed right here that does all this stuff you see flying by. This is the X-ray diffraction part of it that tells how rocks are put together. This vehicle will launch next November. It weighs about 700 kilograms, 1,400 pounds. We will land it with the most powerful system, and the imaging system at the top, I'll just point to it up there, is inspired by James Cameron's 3D vision that he used to film Avatar. Actually, Cameron's on the team. So we will be able to do wide, stereoscopic pan zooms, looking over our shoulder, and all that kind of stuff. Now, we can't get the data back the way he would when he filmed Avatar in New Zealand, because Mars is, unfortunately, rather far away. But we will get pieces, and he will make Mars the movie in 3D as part of his job to bring Mars to you. And the other reason for that imaging system is by having that wide field of view, we can better plan where we want to go. MER is like looking like this and hoping once a day to get a picture back we plan. This will look at the room the way we see it, and we can dial in 10x. So I could look back and see what the camera guy back there is doing, make sure he's not making fun of me, it's okay, and check it out. We can do that with this vehicle. So MSL is our first mission to search for the building blocks of life. Sometime in the next 10 or 15 years, the next part of the legacy of getting to Mars will happen. Before we send you to Mars, most engineers and scientists believe we have to go to Mars and bring back a piece of Mars to Earth, intentionally, the right piece, safely. That it will be the most complicated robotic mission ever done by women and men. Seriously, it's tougher than Hubble. And this is what it might look like. The Mars Sample Return mission is a favored mission in the planning for what we do to planets with robots for the next 15 years. We will land a vehicle that will descend to Mars in a place where we think the materials, the rocks, will tell us things about whether Mars was ever alive. It will land using a Sky Crane on a big lander. The lander, in this case, will carry a small vehicle to sample the rocks, and then basically a cruise missile-like rocket to blast the samples back out of the Mars atmosphere, 40% the gravity of the Earth, and put them on a place where we could go get them and bring them home. This will be an incredible mission. You can see the rover, communications gear. This is a solar-powered mission, we hope, to save some money. Little fetch rover to go get the thing, and then the rocket to bring the thing back. This will be an amazing mission. This is an artist rendering of what we hope it will look like. You guys will see the results of that class of mission. Now someday, and I can't vouch for the date, someday the first human mission to Mars will occur. Whether it looks like this international mission here coming in on this kind of vehicle, I can't say. It would be silly for me to design it for you today. You guys are going to have to design it. But our president said on April 15th, Mars is the goal. And while these guys look a little unhappy in their landing, I think if you were going to Mars for the first time as people of planet Earth, I think you'd be rather excited because it's a big place. You're not going to get stuck on Gilligan's Island if you get to Mars. Plenty of stuff to do. It's like an amusement park for science and engineering. So how we land, don't know. This is one model. Here's a couple of women and men wandering around the surface. But needless to say, getting people there will increase the pace of how fast we learn about living off planet and going to other worlds beyond anything I can tell you about. Seriously. But I thought I'd finish in my last 2 minutes, if you will give me one more second, to show you what it might be like if you or I were to go to Mars. So Mars is Rising. This was a program on Discovery Channel and other channels as well. So we decided to go and try to bring Mars on Earth to you. So I filmed this with some colleagues. This is the newest land on Earth, the island of Surtsey off the coast of Iceland, formed in the 60s from volcanic eruptions from 200 meters deep water to make new land. Here's what it looks like coming in. We actually had a cameraman hanging out the window of the helicopter, not the safest thing. Here's gullies that formed in the rocks that formed from that stuff. The seaweed, of course, we wouldn't expect on Mars. These are gullies, just like we see on Mars. This is what they would look like. So imagine trying to traverse those yourself in a spacesuit where you don't want to fall down, wouldn't be good. You don't have a lot of time, you got to do a lot of work. And this is what it would look like to go up through a cross-section of the kind of gullies we might find on Mars. Every one of these layers, where you see bomb sags and all kinds of volcanic stuff, could contain chemical tracers, as you see even here. There's me, showing the sign with my Mars pen, showing the signs of life. Yeah, I know you're laughing. It was actually a warm day. This is what we hope to find. This little zone, this steam vent with this green smudgy stuff, is the kind of place that some astrobiologists think life could have sprung forth on Earth. We could have had hot vents, and the crusty things here are actually colonies of cyanobacteria growing in a place that did not exist 45 years ago. So Surtsey is the kind of place where we get in one little area a microcosm. In other places in Iceland, which are amazingly accessible as a place to think about Mars on Earth, you can wander right up to a place where the geothermal energy that makes new crust under the ocean in 40,000 kilometers of mid-ocean ridges comes on land. So we wandered right up to these places that would be roped off with chains and guns and other places, walked right up to them to sample the materials. This would be our dream for Mars. These hot springs we find in places like Iceland, Hawaii, deep in the seafloor, here blowing steam and gases, are the kind of place where some scientists believe life could get its cradle. It's warm, it's wet, it's full of energy, it's full of nutrients. There you see a little microvolcano. That's my finger going over it. All of these are interesting minerals involving sulfur and iron, the bubbling mud pots. Again, we think we see mineral expression of these kind of things like that on Mars today from orbit. So if that happened from orbit, and we can see it, then what's it like when you go up close? Well, we don't know. We haven't been. They're harder to get to. But MSL has the tools, and there I am sampling a big colony of cyanobacteria, my name on my hammer. This is billions of single-celled organisms growing in a slime across a hot geothermal vent in Iceland. We have similar things in Yellowstone, in the Azores, and other places. So let me finish with the following thoughts. I'm going to finish, if you don't mind, with a little bit of art history. In 1958, a famous American painter known as Georgia O'Keeffe painted this picture, The Ladder to the Moon, from her house in Taos, New Mexico. She was a modernist, worked with Stieglitz and others, if you know our history. She painted a lot of things that are kind of neat, skulls of cows dying in the desert. She painted this too. It was painted on the eve of the formation of NASA. Very interesting. She exposed it for the first time in the late 50s, right as NASA was born as an organization. Now, you guys are all young. It's a long time ago, the 50s. They were all nuts. Okay, understood. But her vision for that painting, A Ladder to the Moon by People, was resolved within a decade. Within a decade, Americans flew in orbit around the moon on spacecraft, Apollo 8. And within another year, we landed on the surface of another world. No human being has been back since. So she left a legacy in art. And the question to you all to think about, as many of you embrace your careers and your interests over the next 30 or 40 years, where do you want to go? Where do you want your generation to take the people of planet Earth? Lots of places to go. The legacy in space is an interesting thing. We live in space. Our planet is pummeled by cosmic collisions, by the effect of the sun, by how our planet was even potentially seeded with the building blocks of life. We don't know the answers. But there will be a new ladder by some new artist and group of engineers and scientists like you that will take us somewhere. There's the moon, seen at half phase from New Mexico in 1958, a long time ago. What will be next? Our president on April 15th said, That's your goal. It's a hard goal. It's a worthy goal. The first nation or group of nations that get there will have boldly changed the way technology is done. And I don't know how you'll go. But if you choose to go, I promise you, because I've studied Mars my full lifespan, I promise you, you will find something literally earth-shattering. So it's a big solar system. We started with our own planet and looked at a lot of these worlds. Enigmatic Venus, tempting Mars, our own world. A lot to learn. But I think now is the time, in this time of scientific revolutions on these worlds, to think about where you're going to go. So the science is ready. I hope you're ready. Thanks very much.